Hi guys, in this section we are going to study differential equations, or at least we're going to have an introduction to differential equations. You can have an entire course on differential equations, but we'll just have a series of a couple of lectures just to get us acquainted with the concept. So a differential equation um, is really any equation that involves derivatives, and you're going to use the derivatives to try to solve back for the original function. The type of differential equation that we're going to be studying in the next several lectures is where the rate of change is related to the amount of stuff that you actually have. So as an example of this, maybe the rate of change of a chemical process depends on how much of the chemical you actually have in your solution. So in this lecture, what I'd like to do is just introduce what it means to be a solution to a differential equation. Then in subsequent lectures, we'll see how we can actually find solutions. And then finally, a couple of typical applications involving differential equations and the sciences. So let's start out with an example, just to try to understand what it means to be the solution to a differential equation. So let's let y percent be the percent of all possible 125 integral problems a student can solve. So, and we're also going to say that dy dt, the rate at which a student learns, follows a pretty typical model, which is fast at first. It may not feel that way, but since you know nothing at the beginning, you're actually learning quickly at first, and then as the process matures, you actually slow down the learning rate. So what might that look like? So one possible way of sketching this is if we imagine 100% up here, and let's imagine that we're never going to be able to solve every single problem. I know I can't. If you're learning faster and faster at first, then at first you know 0, and then you're going to slow down the learning as time goes on. So time is my axis here, and the percent is up here. So I claim that dy dt, so this is just a claim, dy dt equals 100 minus y could potentially be associated with this picture. Well, let's see. Let's plug in a couple of numbers. If y equals 10, then dy dt is equal to 100 minus 10, or 90. If y is equal to 90, dy dt is equal to 100 minus 90, or 10. So when I know a little bit, I'm learning fast. When I know a lot, the rate at which I'm learning is slowing down. Okay, so this seems like an equation that could potentially model this situation. I have another claim. So let's not call that a claim anymore. So this is going to model this. My new claim is that y equals 100 plus c e to the minus t is a solution. So this is going to pop up more, especially in your homework problems. Maybe there's more than one solution to differential equations. That shouldn't surprise you, because the solution to a differential equation is going to be the function related to the derivative. But again, we're going backwards. We're taking antiderivatives, so maybe there's more than one possible solution. So my claim is that this is a solution. So I want to talk about what it means to be a solution. Well, let's review for a second. If I tell you that I have the equation x plus 2 equals 5, and I tell you x equals 3 is a solution, or in that case, the solution, then that has a meaning. That means that if you plug this in, then the left-hand side equals the right-hand side. So we're going to do a similar check here. For this to be a solution, the derivative of this guy with respect to t should equal 100 minus that guy. So let's check it out. The left-hand side is dy dt, and the derivative of 100 is 0. The derivative of this guy, thinking about the chain rule, is going to be minus c e to the minus t. The right-hand side is 100 minus y. Well, y is 100 plus c e to the minus t. And we could distribute to get minus c e to the minus t. So are those two guys equal? Yeah, they're the same. Therefore, this is a solution. We can actually do better. We can do better because this is going to be a solution for any c value. However, we also have an initial condition. So from my picture over here, I see that when t equals 0, y equals 0. So what I can do now is I can plug this guy in to get 0 equals 100 plus c e to the minus 0. That's just 1. To tell me that c is equal to minus 100 in this case. So the specific solution we have is y equals 100 minus 100 e to the minus t. So again, let me be clear about this. How I came up with this solution is not something that you guys are capable of at the moment. You will within a lecture or so. But you should be able to now understand what it means to be a solution. All right, so let's do another example. Let's say the second derivative. The second derivative of y with respect to t, this is notation for that. If you're taking a physics class, you might see that type of notation, Leibniz notation for the second derivative, plus 4y equals 0. So that's the differential equation, and this guy is called a second order differential equation. Just means that you have a second derivative lurking about. The previous one was, you guessed it, a first order differential equation. So my question is whether y equals 4e to the minus t, is this a solution to the above differential equation? So you guys actually know how to do this now, so I would recommend pausing the video, giving it a shot, and then pressing play again. All right, hopefully you tried to compute the second derivative. So let's compute the second derivative of this guy. I guess we need the first derivative first. So y prime is minus 4e to the minus t. Y double prime, which is the same thing as this guy, is equal to 4e to the minus t. Here I'm remembering to use the chain rule. And let's see, 4e to the minus t, that's this guy, plus 4 times y, that's the right-hand side. Sorry, that's the left-hand side. And the right-hand side is 0. So are those the same? The answer is no, so we would say that that is not a solution. Right, I just want to provide one more example. So for what value of k, if any, does y equal 5 plus 3 e to the kx satisfy dy dx equals 10 minus 2y. So again, I would recommend pausing the video, see if you can figure this out. All right, so we need to take the derivative of this. So dy dx, so this will be the left-hand side. Dy dx is just, well, the derivative of 5 is 0. The derivative of 3 e to the kx is going to be 3k e to the kx. Using the chain rule there, and the 3 goes along for the ride. The right-hand side is 10 minus 2y. And the y is the 5 plus 3 e to the k x. So that's the same thing as 10 minus 10 minus 6, sorry. 10 minus 10 minus 6e to the kx. Okay, and the 10s cancel. So for what value of k does this satisfy this? Well, we need these two guys to be equal. So we need 3k e to the kx to be equal to minus 6 e to the kx. So what I'll do is I'll bring everybody to one side. 3k e to the kx plus 6 e to the kx. Set that equal to 0. Let me factor, so we get e to the kx times 3k plus 6 equals 0. And we need both of these guys, well, we need one of these guys to equal 0, or at least one of them. This guy is never 0. And this guy is going to be equal to 0. Probably can do this in your heads when k equals minus 2. So if k is minus 2, then this equation satisfies this relationship, this differential equation. In other words, it's a solution to it. So that's my introduction to differential equations. Here we developed an understanding of what it means to be a solution in a differential equation. The next lecture, we're going to develop one technique by which we can actually solve differential equations so that we can actually come up with a solution, and then we'll look at some applications. Thanks for listening.